4,500 years ago, ET landed in the Arabian Peninsula or moved across to Egypt and built a set of pyramids. And then 3,500 years later, built some matching pyramids in the Yucatan. In 1947, ET suffered an engine failure over Roswell, New Mexico, and ended up being autopsied in a lab. And in 2012, ET was flying over Kentucky when this amazing UFO video was taken, and I think you're probably all convinced now that we are being visited by aliens. Well, actually, that was Google's attempt to bring balloon-borne Wi-Fi, and apparently their balloon got loose and blew away. There is not very good evidence that we are being visited by extraterrestrials. But nevertheless, people tend to jump to conclusions. So I'd like to start by showing you this artist's impression of all of the planets that were known outside of our solar system 30 years ago. The situation has changed in the last 30 years. And we now know of a bunch of these. Actually, there are planets everywhere. This is 51 Peg B, the first planet to be found orbiting a sun-like star. And the reason why that's an artist's impression is because taking pictures of planets is hard. This is a picture of Saturn taken by the Cassini space probe. So this is a probe that was sent and flew out about 1 billion kilometers out beyond Saturn, turned back and took this picture. I think this is a really incredible picture, not least because you're all in it. The Earth is this little pale blue dot seen from 1 billion kilometers away. And this gives you an idea of how hard it is to take pictures of planets within our solar system, but the closest stars are 1,000 times further away than this, and so getting direct images of planets is really, really hard. It's kind of like looking for a firefly next to a searchlight where you have the bright star and the planet nearby. It's really a contrast issue as much as it's sort of a sensitivity and resolution issue. It has been done. There are some instruments on the Keck telescopes, for example, that have enabled us to get direct images of stars, of planets. And in fact, some of my colleagues at UC Berkeley, this is a grad student, Jason Wang at UC Berkeley, who made this image. You can see this is 7 years of Keck data where you're seeing 4 planets. The innermost planet there has an orbit of about 40 years. You only have a partial orbit as it's going around. The outermost planet goes around the star once every 400 years. And so we do have direct images in a few cases, but they're really just little pinpricks of light. We don't have much information about these planets. We don't have much information about their atmospheres, if any, and we certainly don't have any information yet about whether life has arisen on any of these planets. But what we have learned in the last 30 years, in particular thanks to missions like the Kepler Space Telescope, is that planets are everywhere. So there are a couple of ways that you can find planets. One is to look for this wobble effect, essentially as the planet is pulling on its parent star. It's been described as like walking an invisible dog, and you can tell how big the dog is by how much it's pulling the owner around. So you have a little planet, it pulls its star backwards and forwards a little bit. You're actually measuring radial velocity shifts here, Doppler shifts in the light that's coming from the star. And we can get sensitivities that essentially amount to meters per second. So this is walking pace. Essentially, you're measuring the change in the color of my shirt as I'm walking towards you and as I'm walking away from you. Amazing precision measurements that have enabled us to detect a bunch of planets using this radial velocity method. About 600 planets have been discovered this way. You can also, if you're lucky and the orbit of the planet is aligned between the star and the Earth, you can see a planet as it passes between you and the star, and you see the light. There's a light curve there on the left, drop down as the planet transits, and then it comes back up again as the planet has gone past. And by looking at the depth of that transit and the width of the transit and indeed the period between successive transits, then you can determine a lot about the planets, infer their properties, infer their mass, infer how far from the star they are, and then by the properties of the star, infer their surface temperatures. And about 2,600 planets have been discovered this way. This is the method that the Kepler spacecraft uses. So here is, again, an artist's impression of some of the planets, including the Kepler spacecraft. Not all of these are in the same planetary system, but this is sort of an illustration of the planetary zoo that Kepler and other missions have found. And essentially what we're discovering is that planets are everywhere, including planets in the habitable zone where liquid water could exist on the surface. So this is one system, the TRAPPIST-1 system that was in the news a little while back, where there are 7 planets that essentially are kind of temperate, 3 of them in the habitable zone where liquid water could exist on the surface, Everywhere we look, there are conditions that are right for life, and indeed, we also find ingredients for life everywhere we look as astronomers. There's a few 100 billion stars in the Milky Way. Most of them have planets, and something like 1 in 5 of them have a habitable zone planet. So there may be something like 40 billion habitable planets in our galaxy, and that's not to mention habitable moons potentially around gas giants. So we think that some of the moons of Jupiter and Saturn in our own solar system may be good places to look for life, even though those planets are not in the habitable zone. So again, the potential for life is there. Even if life is a 1,000,000 to 1 chance or a 1,000,000,000 to 1 chance, given the ingredients and the conditions, then we still might expect to find life elsewhere in the galaxy. And of course, our galaxy is just one of many. This is one of the deepest images taken of the universe, the Hubble Ultra Deep Field, an average of 20 minutes per position. So this is a deep image, 11 days of total integration time. This region on the sky is essentially the size of a grain of sand held at arm's length, and there's about 10,000 galaxies in this picture. So there are really galaxies stretching out as far as the Hubble can see. This is only 1/13 millionth of the sky, and you can see one star in the center here. There's a few stars. You can tell the stars because they have diffraction spikes here. That star is about 20,000 times too faint to be seen by the human eye. So essentially, this is a grain of sand-sized region of the sky that would appear completely black if you were to look at it with the naked eye. And there are galaxies everywhere. So, there's all these places for life out there, but to paraphrase Enrico Fermi, where is everybody? Well, we're looking. So there's really 3 ways that you could find, that you could seek for life. One is to do in situ measurements. I should point out that the picture at the top was not taken on the surface of Mars, otherwise we'd be done. This picture was in the Mars yard at the Jet Propulsion Lab, where some of the rovers that are driving around on Mars were developed, the Curiosity rover there. Curiosity doesn't have the instrumentation to directly detect life, but it is looking for signs of organics. And again, there are sort of solar system missions that are in the works that may be able to detect signs of simple life in our solar system. And if we find that there, then really we will be convinced probably that life is abundant. Although the question will still arise as to whether it's kind of caught a ride between planets in the solar system or whether indeed it's arisen independently in various places. You can also do remote sensing. So I mentioned how difficult it is to image planets, and getting spectra of planets where we might be able to determine the composition of their atmospheres is harder still. We're going to be able to do this for a handful of nearby planets, particularly with missions like the James Webb Space Telescope, which, fingers crossed, is going to launch in the next couple of years. It keeps on getting pushed back, but I think we're getting close. There's an XKCD cartoon that has the launch date as a function of time, and it's intersecting the 1-to-1 line, I think, at like 20-something, so it should launch. And when it does, and with 30-meter class ground-based telescopes as well coming online, then we may be able to see signs of disequilibrium chemistry in the atmospheres of planets that are maybe some evidence that simple life is modifying the chemistry there. These are known as biosignatures, signatures of biology. But what we're working on in the search for extraterrestrial intelligence, the SETI program, which I should point out is not just based at the SETI Institute in California. It's not just based at Berkeley SETI Research Center at UC Berkeley, but indeed there are people around the country and around the world who are doing SETI research. What we're interested in is looking for life that has become more advanced. And essentially, this is motivated by the kinds of technology that we have ourselves. So instead of looking for biosignatures, we're looking for technosignatures, signs of technology, signs of transmissions, perhaps picking up powerful radio, perhaps picking up powerful lasers, way more powerful than these lasers that are illustrated here and used for astronomy, but maybe lasers that are used for propulsion or for communication. Perhaps sort of more fancifully, you can see an illustration of a megastructure down here on the left. Maybe an advanced civilization might actually be building huge structures around the star that modify the light of the star. But essentially, we're not trying to put too many prerequisites on this. We're just trying to go out and do an experiment to see if we see any evidence of artificial transmissions or structures or propulsion that could be attributed to an intelligent civilization. And it's worth pointing out, actually, that although making images of planets is hard, and although we have this contrast issue in terms of looking for biosignatures, actually the Earth outshines the sun in certain narrow ranges of frequency. So at certain radio wavelengths, and indeed if you had a powerful laser as well, the contrast is there. So it's just a very small bandwidth, but if you're tuned to the right band, then actually the contrast issue kind of goes away. And in particular, with powerful enough transmitters, if you had a dish like Arecibo, and we're using that to transmit, and then you have a receiver like Arecibo at the other end, then you could communicate on distances of hundreds of light years across the galaxy. You have sufficient sensitivity. So a lot of people think that this is what we do, or maybe they think this is what we do. But in actual fact, what we do is a lot more kind of based in science, and it's really kind of akin to a lot of what we've been talking about here this week about the GNU radio stuff. We just kind of scale it up a little bit. And I like this quote from Carl Sagan and some co-signatories in Science magazine, that really we just have to go out and do the experiment. We actually have to go out and make measurements and see if we can find something. So you're all familiar with this. I show this to public audiences, and I've done some demos with software-defined radio, kind of showing that you can tune to FM stations, showing that you can pick up car keys. Kind of one of the things that I like to say to people is, there are radio stations that are transmitting in languages that I don't speak, but I don't have to speak that language in order to ascertain that there's some intelligence there, right? That somebody is sending me a message. And similarly, if we can get beyond human language and get to the language of math, if I send a series of pulses, this is kind of, for those of you who have seen Contact, this is sort of part of the theme of that movie as well, that perhaps, we don't need to actually understand the transmissions, but we could recognize them as artificial. And so we can do that. We can do sort of tabletop demos with software-defined radio. We can also, as I'll talk a little bit later, use software-defined radio actually to help with the research. But we also want to scale things up a little bit. So instead of a small antenna and a $30 SDR that you can pick up on Amazon and make plots like this, these waterfall plots, which you're all very familiar with, we're going to scale things up a little bit. And thanks to the generosity of sponsors at the Breakthrough Prize Foundation, I don't know why my boss had me do Fox Business, but this was at the launch of, around the launch of Breakthrough Listen in 2015. I think the $100 million was the thing that really got them excited and waving their arms around. And so $100 million over 10 years to really kind of ramp up the search for extraterrestrial intelligence. So what does that buy you? Well, it buys you a bigger antenna for a start. So we have 20% of the time on the Green Bank telescope, the largest steerable dish, which you've heard a little bit about yesterday as well, the Green Bank Observatory in West Virginia. We also have about 20% of the time on the Parkes radio telescope, which is the largest radio telescope in the southern hemisphere. We have time on an optical telescope at Lick Observatory, the automated planet finder, to look for laser signals. And we're ramping up as well engagements with other telescopes around the world. Now, you can't plug this into, well, I guess you could plug this into a $30 SDR. It will be a little bit of a waste of the capabilities of the telescope. So instead, we built a cluster at Green Bank. There's a couple of papers here describing the infrastructure at Green Bank and at Parkes, and telling you a little bit more about the details of that. So we have 6 gigahertz of instantaneous bandwidth. We can get down to 3 hertz resolution. So this obviously generates pretty large data rates. There's 4 petabytes of storage on site, although that would fill pretty quickly with 20% of the time on the Green Bank telescope. So each of these boxes here, each of these compute nodes is writing 750 megabytes per second to disk, and again, we're observing about 20% of the time. So the raw data rates are hundreds of terabytes per day for now kind of over a couple of years. So this fills the disk pretty quickly. This is kind of the raw IQ data, basically. And so we have to reduce that to make spectrograms, to make essentially waterfall plots. And we're typically using the waterfall plots for analysis, although we're scaling up to deal with these data rates. And for any of you who are interested in helping us scale up to deal with these data rates and have real-time algorithms that are running on this, then this is something where we're really actively pushing right now. And then we're archiving data. We have some of the raw data archived. We have some of the waterfall plot data archived as well that you're welcome to go and download and have a play around with. Thinking about the search space, so this is a plot that essentially on the axis that's kind of disappearing into the screen is showing the frequency range of surveys that have been done so far. And then on the the axis that's sort of horizontal and pushing up to the left, the fraction of the sky that's been covered, and then the height of the bars is sort of in arbitrary units, the sensitivity. So taller bars are surveys that were more sensitive. And essentially, this is just to illustrate that there are some trade-offs, right? You can do a very sensitive survey like Project Phoenix, the red bar there, that covers a very small fraction of the sky, but some range in frequencies. Or you can do a survey like these Serendip surveys or the meta surveys, which are a very narrow range of frequencies, but are covering a larger fraction of the sky and maybe less sensitivity. But there's these trade-offs that essentially amount to how much time you can get, how big the telescope is that you can use, and how much data you can handle. Well, Breakthrough Listen is kind of changing the game here. So we have a targeted survey that is focusing on individual stars, so that's still a small fraction of the sky, but it gets us good sensitivity over a very wide range of frequencies. And then we have surveys, particularly with the Parkes telescope, where we're scanning across the galactic plane, smaller range of frequencies, but getting a lot of imaging there, a lot of spectra, essentially, which amount to image-like data, but that's the data that we're archiving. And so here is one of these waterfall plots from the instrument at Green Bank. So this is the output of one of those compute nodes. There are now 64 of those compute nodes out at Green Bank. Each of them gets 187.5 megahertz of the band. So actually, I misspoke when I said 6 gigahertz of bandwidth. As of a week or two ago, we now have double the capabilities there at Green Bank. And this is 5 minutes of data. The vertical black lines that you're seeing here are the coarse channelization. But you can see some signals that are coming through here. The sensitivity is kind of arbitrary and not calibrated. And of course, we're picking things up. And going back to the early SETI experiments that were done by Frank Drake at the Green Bank Observatory in the early 1960s, I think the first time they turned their chart recorder on and saw something, they thought, well, can it be this easy? Well, of course it's not. You know that even back in the 1960s, RF signals were still around and not, the number of them that were coming from ET was vanishingly small compared to the number that are coming from our own technology. That's still the case. We don't know whether they're vanishingly small or zero. That's the experiment that we're trying to do. So how can we ascertain whether these are candidate extraterrestrial signals or not? Well, there's various ways, and again, we're working on this. Right, so there are signs of intelligent life all over the place. The reserve bands for radio astronomy are pretty small. We're not just doing surveys at 21 centimeters anymore. As I mentioned, we're doing large amounts of the band, and so we pick up a bunch of interfering signals. Even in the National Radio Quiet Zone around Green Bank, where fixed transmitters are restricted, there's still satellites going overhead. There's still people trying to get Wi-Fi signals and using garage door openers. Microwaves, you should look this one up if you're not familiar with it, kind of an embarrassing result from the Parkes telescope a few years back that turned out to be somebody who was impatient to get their lunch out and popped the door open, and the telescope picked up the microwave signal, and they thought it was coming from space. They later ruled that out, but it's kind of a good story, actually. It's sort of a good sleuthing story. But again, satellites coming overhead are an issue as well. So one way that we can deal with this essentially is to use the fact that we have a very directional antenna. The field of view of the Green Bank telescope at the frequencies that we're using is a 100-meter dish, so we only really get a few arc minutes on the sky. So essentially, by nodding the telescope on and off the targets that we're looking at, we can see if signals are coming and going, and hence try and localize them on the sky, whereas the interfering signals wouldn't be expected to come and go as we do that. So here's that plot that I showed again, just one region of the band that we're recording. Here's what we see when we move off that particular star, the star Hipparcos 93805. This is just the catalog number up at the top, and then this is an off observation where we were pointed about a degree away. Well, okay, now did we see ET? It looks different, but there's nothing kind of really obvious there. So let's do this 3 times. We'll go on in the top left, off in the bottom left, on, top middle, off, bottom middle, on, top right, off, bottom right. And we do 3 of these on-off pairs, 5-minute observations, 30 minutes of observation per star. This is what we do at Green Bank. At Parkes, we have access to a multi-beam system where essentially we can point in different directions at the same time and do interference rejection in real time. And then we can also talk a little bit later, we're scaling up to doing observations with arrays where you can do clever things like putting multiple beams on the sky with antenna arrays in particular. But at Green Bank, we're just kind of doing this on-off nod, and essentially the goal here is, well, do I see anything in the top line that's not there in the bottom line? Because if I do, then that's interesting. So at Green Bank, again, we're writing raw data. We save some of that, but mostly we're writing spectrograms, either in this sort of filter bank format, which is used for radio astronomy data, or now HDF5, which has some advantages in terms of ease of access to the data and data compression. Some of these are publicly available. I'll have some links later in the talk that show where you can go and look at these. We're working on making more and more of this publicly available if any of you want to go take a look at it and download it. The filter bank files that we write out, we have to make compromises between frequency and time resolution. So there's a high frequency resolution, 3 hertz frequency bins, which is kind of a SETI data product because we really want to see the difference between artificial signals. Nature doesn't make signals that are more narrow band than sort of a few hundred hertz. Essentially, there are no astrophysical sources that are that narrow band. So that's one way of distinguishing if a signal is narrow band. There are also reasons to think, just in terms of the energetics, that if you wanted to send a beacon, that you want to put as much of that energy either into a narrow range of frequencies or into a narrow pulse in time, or potentially both. And so the narrowband search is actually kind of motivated as well by the idea of detectability at large ranges. But also it's kind of a good way to distinguish yourself from background noise. And so maybe you might be looking for a carrier, maybe there's a data signal that goes along with the carrier, but the high frequency resolution data products is the one where we've really been kind of putting a lot of our attention so far. We have a high time resolution data product, which is typically what astronomers are using for pulsar searches or for searches for fast radio bursts, essentially things that come and go on short time scales. And then there's a sort of compromised data product in the middle, which is the kind of thing that you would use if you're studying astrophysical spectral lines like neutral hydrogen in the galaxy. So there's a paper by my colleague Emilio Enriquez from last year where essentially Emilio did this on-off comparison. So what you're seeing here is 8 examples where we have 5 minutes on, 5 minutes off, 5 minutes on, 5 minutes off, 5 minutes on, 5 minutes off. And he's isolated here some signals that are Doppler drifting, and so he does a Doppler drift search, essentially, again, as another kind of cut to get rid of some of the contaminating signals. You would expect something in the same frame as the telescope to just be a vertical line in these plots, but if you have a transmitter that's on a rotating planet that's being picked up by our receiver on a rotating planet, then there should be a Doppler drift there. So if ET was sending a beacon, then you would expect to see a diagonal line that cuts off in the off observations and then comes back when we move back to the target star that we're looking at. And so these were sort of, he found 11 of these kind of signals of interest. We don't think any of these are ET, in particular because they're all around the same frequency and they're all in regions of the spectrum where we see a lot of radio frequency interference. But this is sort of a proof of concept, essentially, that, okay, we can do this. We'd like to do this in a more sophisticated way. And we'd also like, when we have candidates like this, then to go back and reobserve them or to get somebody else to reobserve them with another telescope, with another system, and see if they persist. And essentially, if you can track something across the sky, if it's moving at the sidereal rate, if it's going with the star that you're tracking, even a geosynchronous satellite is going to stay at the same altitude and azimuth, and it's not going to track with a star. And so this is a good way of rejecting interfering signals. It's not the only way, but it's a good one. The British tabloid newspaper, the Daily Star, picked up on this and announced alien shock as scientists reveal, I don't even know what this means, 11 mysterious signals hailing Earth are probed for UFOs. Okay. Well, at least we're getting some news out there about the project, so that's fun. But what we really want to do, some of you who've been into the expo next door have seen that DeepSig can do this in real time. You can draw boxes around stuff and put labels on them. And this will be really nice to be able to kind of identify these signals and to see which ones are persisting, and then to see if there's anything that's showing up essentially in the top row there that looks either like it's just in the top row or that looks unique, that essentially looks like an outlier in some way. And outlier detection is also something that we're pretty interested in working on. So if I was ET, then what I would do is transmit something like this. I'd put kind of smiley faces in the waterfall plots. I'd do something that is really obvious and looks nothing like the other signals that are out there. maybe they're doing this, and we haven't found it yet. We have a lot of data, and if you imagine a Doppler drift search, essentially you have a matched filter here that's looking for diagonal lines. It might not do a very good job of, I mean, it probably would pick those up, but it might not do a very good job of finding something that is sort of close to the threshold, above your signal-to-noise threshold, but essentially is sort of a more complex signal that the simple searches are not as likely to pick up. So we can pick up simple signals, relatively simple signals. This is an example of a fast radio burst. This is from the detection of the first fast radio burst by Duncan Lorimer and collaborators in 2007. And these were the ones, incidentally, that people got worried about the microwaves, because the microwaves gave a similar kind of signal, but actually isolating these things on the sky turned out to be the thing that distinguished between the peritons, as they were called, these signals that ultimately turned out to be the microwave ovens, and the signals that really are astrophysical. There now is pretty conclusive evidence that many of these fast radio bursts are coming from distant galaxies. And so this is the discovery paper. So essentially what you have here is a pulse that is sort of a millisecond or so long, emitted at a fairly broad range of frequencies, and then it propagates through the interstellar medium and through the intergalactic medium as it comes towards Earth. The lower frequencies get delayed in their arrival time relative to the higher frequencies, and so you get this characteristic chirp shape, this quadratic chirp. And actually you can measure a dispersion measure, which is the amount of chirp that there is in there, and infer the amount of material between you and the source. Again, assuming that it was all emitted at one frequency at once and now is received as a chirp. And the chirp is shown in the grayscale there, and then the de-dispersed pulse is shown as the line graph there to the top right. So essentially by fitting for that quadratic dispersion and undoing it, then you can determine the properties, the intrinsic properties of the emitted pulse. The amount of dispersion that's there in these pulses indicates that these things come from intergalactic distances, but it actually took observations of one of these pulses, which repeats, to be able to isolate it, to be able to find the host galaxy, which turns out to be several billion light years away. So that then gets you the energetics of these things. So the distance, so the measured distance of this galaxy actually matches what we're seeing from the dispersion measures for these things as well. And the energetics are really huge. It's actually kind of a problem for the physical modeling of these things. What is the progenitor of these fast radio burst pulses? Here is the host galaxy. It's a little kind of scrap of a galaxy here, isolated by using interferometry with a very large array, where they're able to pinpoint the position of a persistent radio source on the sky. But this galaxy has been, or the object in this galaxy has been emitting a bunch of these pulses, and it's the only one so far that's known to repeat. So it's pretty interesting. Are there two classes of objects? Do all of the other fast radio bursts that have been found repeat? Or is this unique or a member of a different class? And that's one of the things that we're trying to find out. So our group at Berkeley, this was a paper, again referenced there, led by Vishal Gajjar, who's a postdoc in our group, published a paper earlier on this year where they found a bunch of pulses that were coming, 21 pulses that were coming from this repeating fast radio burst. Apologies, the axes on some of these plots are inconsistent, so you've got frequency going from top to bottom there, but you see again this characteristic chirp shape. And these are just a bunch of these pulses that were picked up over the course of, this was a couple of hours of observation. All of these pulses were seen in about half an hour of data and pulled out by this code called Heimdall, which is a GPU-accelerated de-dispersion code. So essentially it just fits a range of possible dispersions and then maximizes signal to noise and spits out when it finds a detection. Again, the Daily Star was quick to pick up on this. Scientists say monstrous energy bursts from space, maybe from aliens. The boffins at Breakthrough Listen confirmed, picked up the strange signals. So that's that. It turns out that Google is pretty good at finding ET. You just type ET into Google image search, and you can even find ET meets Mr. T down here. I like that one. And so can we apply essentially the sort of image recognition techniques, and we've heard a little bit about machine learning as well here this week. Can we train algorithms to find things that we're looking for in the data that maybe are missed by classical algorithms? Can we train things that might pick up some outliers? Well, yeah, it turns out we can. Jerry Jiang here. Can you raise your hand, Jerry? Jerry's going to be around for the next couple of days. I have to take off basically after this talk, but Jerry would be happy to talk to any of you who are interested. I'd be happy to communicate with folks over email as well. But Jerry had some very nice work where essentially he inserted 100,000 simulated bursts, these quadratically dispersed chirps, into real data from Greenbank, trained a convolutional neural network on these, and you can see the black line here is the signal-to-noise cutoff for Heimdall, this kind of classical algorithm which just does that fit. And Jerry, with these other curves here, was able to find a lot more bursts, in fact, 72 more bursts at lower signal-to-noise. And the nice thing is that when they looked at other data that wasn't coming from the direction of the repeating fast radio burst, they didn't find any. So this is really nice kind of validation that these bursts are real. Jerry has a poster that will be up again until they're taken down later today, and you should go talk to him a little bit more about this. And in fact, so these are in red, the bursts that were picked up by the classical algorithm, and in white, the bursts that were picked up by Jerry's CNN algorithm. Some of these have a smaller range in frequency than the ones that were picked up by the classical algorithm, which is why there were issues with them rising above the signal-to-noise threshold for the classical algorithm. But essentially, by studying these, it tells us more about the astrophysics of these fast radio bursts, but also it's sort of a proof of concept for what we can do for the SETI search, and that we want to develop algorithms that are going to find and classify a wider range of signals in the data and to look for outliers. Jerry and an undergraduate student working with us at Berkeley, Morad Schaefer, have also done some modulation classification. They participated in the Army signal classification challenge that we heard a little bit about as well. Jerry, do you have a poster on this one as well? Yeah. Jerry has a poster on this one, but he can talk to you about the other one, or you can read the paper. This again is something that we're interested in. Can we classify the signals that we pick up and essentially sort of find this needle in a haystack by getting better at classifying the hay and throwing it away? So we have actually found extraterrestrial intelligence. This is not as much of a bombshell as it might seem. This is the Voyager spacecraft. I mean, it's kind of terrestrial, but it's kind of extraterrestrial, if you'll bear with me a little bit. I mean, it's 12 billion miles away. It's the most distant human-made object. The transmitter's about 20 watts, so same power as a fridge light, and it's picked up really clearly by the Greenbank telescope. I mean, it can be picked up by smaller dishes, obviously the NASA dishes that are used, like the DSN dishes. But this is a nice illustration, essentially, that there's something that's out there in the distant solar system. We just have to do this at ranges that are kind of 1,000 times further, and then problem solved. Well, maybe their transmitters are brighter. If an advanced civilization has powerful transmitters, then maybe we could hope to pick those up. But essentially, this is kind of the bread and butter of the search here. So we can do a little zoom in from our data here. There's actually a Jupyter notebook. If any of you want to go and download the Voyager data from Greenbank, there's a little tutorial. We've done this with our students as well. You can work through and download it and kind of zoom in by a factor of 3,000, zoom in by another factor of 30, and you can pick the carrier and the data channels up pretty clearly there. Maybe some of you might want to have a go at demodulating some of this as well. Here is a screenshot of that Jupyter notebook. Oumuamua. I think the Hawaiian translates roughly as a messenger from afar arriving first. This was the first interstellar asteroid that was found in the solar system. Some people got pretty excited because it looks a little bit like the spacecraft from Rendezvous with Rama. The axial ratio is pretty weird. This thing was found, I guess this was towards the end of last year, and we decided, well, we should look at it. We don't think that everything weird is ET, but as the biggest search for extraterrestrial intelligence, we should probably point the telescope at this. So we had a quick report on this where essentially we get sensitivities that could pick up a cell phone on the surface of this asteroid at sort of a distance of a few times the distance from the Earth to the Sun. So that's also pretty cool, I think. And the Daily Star was right there. It's kind of hard, when you're talking about ET, not to get the sort of tinfoil hat brigade excited. But I'm glad they're reporting on this. It's kind of fun. So if you're interested, again, we'd really love to kind of engage with people who have signal processing experience, who have machine learning experience. There's a small team at Berkeley of scientists and engineers, but we're trying to make as much of the data public as possible. We're trying to make the code public. We're trying to develop code. If you go to this link, then you can see sort of a tutorial that I've written, which has some links to the data. I have a link to the slides as well if people want to download the slides at the end that I'll leave up. But this is sort of a basic tutorial, and then you can get in touch with us if you need more in-depth, if you need more data, if you want us to stage some particular data for you somewhere on the public data servers. If you just want to kind of have a chat with us, get added to our Slack channels, any of this, we'd love to collaborate. If any of you happen to be in the UK at the end of next month, we have a meeting about Widefield Radio SETI, and so this is the idea essentially that we want to be doing all sky, all the time, as many frequencies as we can, good sensitivity, machine learning algorithms, real time. We want all of this. And if any of you are interested, really, I think anybody in this room would be welcome if you want to register for this meeting. There's no registration fee. You get a tour of the Square Kilometre Array headquarters on the Monday afternoon. And then we have a couple of days of sessions where we'd welcome talk contributions. There's going to be limits on the number of attendees, but again, please reach out if you're interested in attending. So this is a picture that I took up in the Redwoods near where I live in Oakland, California. And if you go hiking in the Redwoods, you'll see some signs there that warn you there are mountain lions out here, there are snakes, there are other kind of things that you should look out for. But I don't see any mountain lions in this picture, so there must not actually be any mountain lions out there, right? I think that would be foolish. Now, I also don't think there's a mountain lion hiding behind that log or behind that particular tree. I don't think the next place that we look is going to be where we find the mountain lion any more than I think Oumuamua was likely to be hailing us, like the Rendezvous with Rama spacecraft. But if we go out and look hard enough, if we do a search, if we do a thorough survey, maybe we actually do a very thorough survey and we find nothing, and that's telling us something. That might tell us that the mountain lion population is smaller than we thought. So we're trying to do the world's largest search for extraterrestrial intelligence. I think we're doing a pretty good job with the resources that we have, but we could always use some more help from you all. If you want a copy of these slides, obviously they'll be posted online, but you can also just grab them from this QR code here with all of the links. You can follow us on social media. You can email me. There's, again, that tutorial there. Visit our website. Thank you very much again for the invitation, and I'd be happy to take some questions.
Thank you very much, Steve. All right, so while we do questions, Robin, if you wouldn't mind getting lavaliered. Oh, great, perfect. If you could switch laptops. Awesome. Sebastian, you have the mic. OK, what questions? Oh, right, Adam.
Okay. Sure.
All right, so I had two questions for you. The first is if terrestrial emissions are an issue for false positives, what prevents you from just doing some sort of localization and just throwing out everything that comes from Earth? I mean, you should be able to use multiple telescopes or whatever to do even just crude localization estimates and say, yes, this is from space, this isn't from space.
Yeah, I mean, essentially that's what we're doing by doing this sort of nodding on and off, or by doing the multi-beam observations. Some people have also proposed, well, maybe you should have kind of an outlier antenna. Maybe you could even like hook up a small disc cone antenna to an SDR. The problem with that is, with a disc cone, that it's not going to be, the sensitivity is grossly mismatched, and also kind of the whole signal path through the instrument. We don't have so much in terms of multipath with the Green Bank telescope, but I think the problem actually would be kind of matching what you see in something like an SDR to what you see in the data from the telescope. So actually using the data from the telescope itself, and again, particularly things like multi-beam and using arrays of telescopes. So we have some pilot programs that are using arrays. For example, a Murchison Widefield array in Western Australia is 128 tiles. These are just dipole antennas operating at 80 to 300 megahertz, and you can form multiple beams on the sky and use that for interference mitigation. So yeah, we definitely want to sort of to localize stuff and get rid of it. The question is really kind of what's the best technique for doing that.
Okay, and then my other question is finding objects in images, like in spectrograms, is like what machine learners do, right? I mean, this is you take your first machine learning class, you're finding objects in images, right?
Yeah.
It's been going around for a long time. Just curious, there's a lot of knowledge out there, right? You said you use a CNN. I mean, there's Huff transforms, there's all this stuff. Have you been pulling in pure CS guys who do that machine learning to help you find these objects and images?
We have been talking to pure CS guys. I mean, we're a university program, so hiring those guys and competing with Google and Facebook is a little challenging. That's one of the reasons why, we come to meetings like this and hope that somebody, with a few spare hours on a weekend might like to kind of have a crack at this. Yeah, I mean, we have some CS people. Obviously, Berkeley is a great place for CS. I know Jerry has collaborated with some of these people. We have students from CS and electrical engineering majors who have come and worked with us, but there's always more that we could do.
So if somebody contributes, can you get a piece written about them in the Daily Star?
Oh, I imagine so, yeah. Even better, I mean, you could get a fraction of a breakthrough prize, which is more than the Nobel, as the director of the Breakthrough Initiatives is proud to point out.
Awesome. Do we have any other questions? What's up, Ian?
Just looking at the volume of data you're collecting at Green Bank there, I'm kind of wondering, have you any gut feel for, if you had, I'm just kind of wondering what disconnect you've got between how much data you can record in a day and how much you can actually imagine processing that data if you had an infinite budget or infinitely powerful hardware. Based on the ideas you've already got to how to process that data. I mean, how much of a disconnect is there? How much do you think you just throw away because you just haven't got time to do something with it before you're going to collect the next day's data?
Yeah, no, that's a good question. I mean, we do have, so I mentioned this paper by Emilio Enriquez where we did a thorough analysis of a large fraction of the data sort of that have been taken over a year of those waterfall plots in a search for Doppler drifting signals, which is computationally far less expensive than a real-time ML-driven search on the raw IQ data that's coming in. Now that, I think that is still way beyond us. I mean, interestingly, actually, Jerry and I were chatting about this and looking at the DeepSig demo yesterday, and I think Jerry was saying, if we got a couple of hundred GPUs going on this, then we could probably do the real-time classification, right?
Hi, yeah, thanks for your question. So it's a great question. So we do record all of our waterfall plots, so the spectrograms, but these are essentially averaged down a factor of 100. So we don't have the disk space to store the IQ data. So we are trying to tap into some of these other technology, for example, real-time signal recognition in IQ data that would help us essentially probe things that we might be throwing away when we do this averaging.
But we're a ways off this yet in terms of, I mean, Moore's law helps, although actually kind of GPUs and RAM have not been falling in prices in the past few months as much as we'd have liked. But hopefully that's a little hiccup on the road. And the algorithms, of course, are evolving at breakneck speed. So I think sometime soon we hope to be doing kind of more sophisticated analysis on the data as it's streaming in. But yeah, for now, kind of a lot of our focus has been on these archival data products.
We have one back there, Sebastian. All right, this will be our last question.
I appreciate it's a challenging scheduling question, time on the scope, where you can look. I was curious, though, how much you're able to choose where you look. You spend a fair bit of time talking about potentially habitable planets. Do you get to look at the stars with potentially habitable?
Yeah, so it's interesting. On the Green Bank and Parkes telescopes, we have 20% of the time, actually the Breakthrough Prize Foundation has purchased time on those telescopes, so we have full control as to where we're pointed, what stars we look at. There's a paper, Howard Isaacson and collaborators, where he describes the sample selection for this targeted survey, which is largely nearby stars. The reason why we pick nearby stars is, again, just in terms of the energy requirements for a transmitter, that's more favorable. In terms of targeting, yes, we have systems that are known to host planets in there, ones that have been pulled out of surveys by Kepler and other spacecraft. But thinking back to the beginning of my talk, if you go out this evening, and well, not that you'd really see much of the night sky in Las Vegas with the giant, thing shining up from the pyramid and that kind of thing. But if you were to drive out into the desert and find 100 stars, 20 of them have a planet in the habitable zone. We don't know which 20, but we might as well just look at all 100 of them. And so we're trying not to be kind of too prescriptive in terms of where we look. The other thing is that with the next generation telescopes, with these aperture arrays, with things like the Murchison Widefield array and other telescopes, essentially you just put a tap in and get a copy of the raw data. The MWA has a field of view of 1,000 square degrees compared to the Green Bank telescope, which is very good for, it's like a kind of looking down a drinking straw, studying a very small region of the sky, but you can phase up and form a beam anywhere within that field of view. So somebody else could be doing completely different surveys, and you just get a tap, you get a copy of the data, you adjust the relative delays and phases, and then you get the data on the object that you're interested in. So that's kind of the way that we're moving, really, is towards these surveys that kind of piggyback on astrophysics.
Let's thank our keynote speaker. Thank you very much, Steve.
Thanks.